We are team number 24-3 and we are working on problem statement C, which involves the design of an active RC biquad filter. So this is schematic of the filter with this added in multiplier over here. So as you can see, there are 3 op-amps and 1 multiplier. This multiplier essentially controls the bandwidth of the filter, and the input is given on this node and the output is taken from the output of this op-amp. So it's this node, and the response from this node to this node is essentially low pass, and so yeah, this acts as a second order low pass filter. One of the problems we faced while designing this on the board was this resistor, because each of the op-amps had only 2 resistors connected to the input terminal and negative input terminal, and to tap this resistor out we had to tap out the resistor from another op-amp. So yeah, going to the circuit. Yeah, so this is the setup of the circuit. This red wire is the input and the black wire here is the output. We've used 3 op-amps over here and this extra resistor over here for the input. Yeah, so this is the oscilloscope response. We are testing at 30 Hz right now, and the blue waveform is the input and the yellow waveform is the output. As can be seen, both the blue waveform and yellow waveform are having a peak-to-peak voltage of around 2 volts, and these 2 divisions over here correspond to 1 volt and the 2 divisions below correspond to another 1 volt. So there's a 2 volt peak-to-peak difference. Now I'm increasing the frequency, and oops. So I increase the frequency. This is around 63 Hz now, and as can be seen, you can see peaking in the yellow waveform. The blue waveform is the same, so it terminates over here. This yellow waveform slightly increases in magnitude, which is the peaking in the low pass response, and the peaking is of the order of Q. So I increase this frequency even more, and the peaking becomes even more visible. And after some time, the yellow waveform starts decreasing in amplitude. So now the low pass response starts kicking in. So this is at around 152 Hz. So I keep reducing the frequency. You can see the phase difference is also reducing. Initially the phase difference is 180 degrees, and now the phase difference is closer to 90, and right now it's about 90. So I keep decreasing this, and so now the phase difference is even less than 90 degrees, and as the frequency of operation of the filter goes even higher and higher, the phase difference goes to 0. This can be obtained from the transfer function, and so the phase changes from 180 degree to 0, and the magnitude changes from 0 dB to minus infinity, and in magnitude this corresponds to a magnitude response of 1, and minus infinity corresponds to a magnitude response of 0. So at infinity, when the frequency is very high, essentially the signal, if it's high pass, the signal is totally attenuated. So this is a digital oscilloscope, and this is an XY plot. The XY plot is essentially the plot of the input on the x-axis, amplitude of the input on the x-axis, and amplitude of the output on the y-axis. So right now the XY plot is almost 135 degree line, line with slope -1, that is, which makes 135 degree with the positive x-axis, and this is because the input and output have a phase difference of 180 degree and have the same magnitude. So this is a characteristic of this filter, and as I increase the frequency, this becomes more and more less and less elliptical and closer to a circle. So now there is this frequency which is around 160 Hz, where this almost becomes circular. So this is close to the cutoff frequency of the filter, and the phase difference between the input and the output is 90 degree at this stage. So I keep increasing the frequency, and it again approaches a straight line, and this limit is when it reaches the limit of a straight line when as the frequency keeps increasing. This again is indicative of a 0 phase difference between the input and the output. So one of the challenges we faced with the cathode ray oscilloscope was we were not able to take measurements for lower frequencies. So this is a digital storage oscilloscope. So as you can see, as frequency is reduced, right now the frequency is 2 Hz, and you can still see the signals very clearly. This is not possible in a Cat 3 oscilloscope, and this is one of the main challenges we faced while testing for the circuit, the characteristics. So this is why we shifted to a digital oscilloscope. And